On number 16, we are to describe how to transform the graph of f into the graph of g, and then sketch the graph by hand and check with our calculator. So the first thing you want to notice is the distinction between f and g, and the only one here is the plus 4, and it's inside. So a plus 4 inside is going to be backwards and move the graph horizontally, so this is going to move our graph 4 to the left. So the first thing we should do is to graph 3 to the x, because we aren't familiar enough with these graphs like we could say a parabola. So we want to graph that first and then move it. So let's move that graph, or let's graph the parent graph first in yellow, just a different color from what we're using for our g of x. And remember, all of these exponential graphs go through the point 0, 1. And then you can go to the right one and up the base, so that would be up 3 for this one. So there's our 2 points that we'll use to sketch it going up to infinity and then coming out and hugging the horizontal asymptote. So now we'll switch back to our blue color to graph g of x. So we're going to take these 2 points that we just found and move them 4 to the left. So the point at 1, we're just going to take 1, 2, 3, 4 steps, and that puts us right here. And then we're going to take the step, the one that's to the right, one step to the right from that graph, that point, and then we're going to move it back 4. 1, 2, 3, 4 would be here. And since that's the only change, that's all we have to do to figure out where our graph needs to be. And we trace out from these 2 points up, and then come back, pick it up, and bring it back to where it comes back and hugs the horizontal asymptote. And that is our transformed graph for 16. On 24, we've got a little bit more going on here. We've got a 3, which is our standard A. And remember, since it's positive, that will just be a vertical stretch. Let's see if I can write that a little nicer. Vertical stretch by 3. And then the -1 outside will move the graph down 1, because remember, if it's outside, it has a vertical effect on the graph. And then the 2 on the inside is a horizontal shrink, because anything inside is horizontal and backwards. So this is a horizontal shrink. Try that again. By 1/2. So again, we'll start with e to the x on our graph. So we'll plot 0, 1. And then we'll go to the right one and up e. And remember, e is approximately 2.7, so I'll go not quite to the 3 and plot that point. And then trace up and out. And come back and hug the horizontal asymptote. And I should have done that in a different color, so I'll switch out now and we'll do g of x in, let's do it in orange just to be different. So we're going to take those 2 points and we're going to move down 1 for each of them. So I'll just put a little dash where those would be if we just move down 1. So the point on the axis would be down 1 there, and the E point would be right about there. We went down 1. And then we have to do a vertical stretch by 3. So, and the other thing about moving down 1 is that our horizontal asymptote would now move down 1 as well. So we'll know what to hug when we move down. So we have a vertical stretch by 3, and the vertical stretch by 3 on the left side is going to do next to nothing. So we can just draw the tail back here, as I like to call it, like that. But then on the right side for a vertical stretch, where we would have gone up to that orange mark, we're going to go up 3 times that. So since 2.7 is E, that would be 8, between the 8 and 9 marks, 8 steps, between 8 and 9 steps up. So that'd be 1, 2, 3, 4, 5, 6, 7, 8 steps up. I would put our mark about right here. But then on top of that, we've got our horizontal shrink by 1/2. So that point needs to come in a half. So I'm actually going to take that mark back off and come in a half from there, and we're going to be right about here when that happens. The truth of the matter is that when you draw these exponential functions, the stretches and shrinks are a lot less obvious, so they're much more forgiving that way than some of the other functions, some of the algebraic functions we've looked at in their transformations. Now let's take a look at number 56. On 56, we are given a population function, P of t, where population is in millions. So you might want to make a note of that when you have a problem like this, just so you'll remember that you've got to realize that if you get, say, 5 for your answer, that it actually means 5 million. And t is years since 1800 on this problem. So that means that for part A, when it asks us to find the population in 1850, that implies that our t is 50. And I don't think I'm going to have room to get all this on the screen, so we're going to back up and erase these B and C, and I'll move those over to the next page when we get to them. So let's look at our P of 50, which is what we need if we're going to find the population in 1850. So we have P of 50 equals, and then you basically just copy everything you see in the function until you get to t and you replace it with 50. That's a decimal. 993 e to the negative 0.035,005, and then we put the 50 where the t was. And then this is a calculator question, and you would never have to do anything like that without your calculator. And if you type that in your calculator, you should get 1.794557. And I included 6 places past the decimal because I know that this number is actually in millions, which means I'm going to move the decimal 6 places to the right. So that would be 1,794,557 people. Then on part B, we're going to do the same thing, but now in part B, we're asked to find the population in 2015. So again, we have to work backwards to know that t equals 0 is at 1800. 1900 would be 100 years, so 2000 would be 200 years plus 15 makes 215 our t value. So we go again. So we write P of 215 equals, and then we copy the function with the t replaced with 215. So we have 19.875 on the top, and 1 plus 57.993 e to the negative 0.035005 times 215. And once again, if you put that in your calculator, if you have an Inspire, you can go back up, copy that down, and change that 50 to a 215. It's a really easy way to do that. We get 19, and again, when you know that your answer is in millions, you should go 6 decimal places of accuracy. And if you do, you get 272,737 as your 6 decimal places, which translates to, excuse me, 19,272,737 people. And then part C asks us, what is the maximum sustainable population? And that is the same thing as the carrying capacity, which is the numerator in the logistic function. So that is simply 19.875 million. So we would write that as 19,875,000 people. And that is our answer to C and the end of this video.